someone tells me, well.
Yeah, in a few minutes, the conference will be broadcasted in live on YouTube. The web address is on the chat. And François, it's up to you now, whenever you want.
Yep. So welcome everybody. This is our great pleasure to welcome you today and to listen to Professor Pierre-Emmanuel Jabin, who is going to present a series of 4 lectures on mean field models. And so I think that Pierre-Emmanuel today will start with some introduction to these types of model, and certainly will give some motivations for this. So thank you again, Pierre-Emmanuel, for having accepted this invitation. This is really a great pleasure to listen to you. I would also like to thank Professor Abal for the organization. He did a wonderful work to have this series of lectures. And also I would like to thank our partners. So Laboratoire Euro-Maghrébin, University Marrakech Sadi Ayad, University Mohammed VI in Morocco, and also University Côte d'Azur. Pierre-Emmanuel, thank you again.
Okay, thank you everyone. And it's a great pleasure to do those lectures, at least now, right? I mean, we might all change our mind at the end. So far, so good. Since this is on Zoom, I'll try to check the chat to see if there are questions, right? But don't hesitate to interrupt me at any point by speaking out if I don't see a question in the chat, for example. Okay, so let's start. And the plan for today is going to be relatively light from the point of view of the math, right? But what I want to go over is show you a few mean field models, explain why we want to do mean field, and all this sort of things. And this is actually a very long and very old story. Because the first type of mean field model actually begins with Newton. So we're talking, right, the 1600s, 17th century, so 350 years ago, roughly speaking. And Newton did a lot of things, right? The one that he has remained probably the most famous for is the law of gravitation. And what does that mean, right? Newton introduces a few very, very important concepts. The first is he does a very big simplification, right? And he brings himself to study point masses. Right. So roughly speaking, what that means is right, gravitation, and he's thinking of our solar system in particular at that time, right? So you have objects, and those objects, of course, can be very, very large, right? The Earth is one of them, and quite a few are even larger, and people knew that already at that time. But their size is much smaller than the distance between them. And so the first thing that Newton says is that he says, well, the size does not really matter, and we can represent the object by points, right? So it's like they are points, and all the mass is concentrated at the point, hence the point mass. And therefore, the objects, right, can be represented in a very simple manner. And you need three quantities to know what's going on with them. Well, you need their mass, right? You need their position. And you need their velocity. And this first point is super important because it's the level of abstraction that we will find a lot in all those many particles and multi-agent system, right? And it leads me to define this concept of a particle or agent. Right. Which is this abstract object that we can represent with only a small finite number of quantities that describe its whole state. Then there's another extremely fundamental point, which is the law of movement. And now we are very familiar with what we sometimes call Newton's law, but at the time, this was not at all obvious. So now I need to have a little bit more of notations, right? So I'm going to consider a finite number of point masses, and I'm going to number them. Right, so I'm going to take capital N of them, and so I'm going to index them, something called I, right, from 1 to N. And then, therefore, I need the mass, right, the position, velocity, and all of this, right? So the mass is going to be MI, right? The position, I'm going to call it xi, and right, this changes in time, and the velocity is going to be vi, right, and this can change in time as well. And now Newton's write down the following system. Sorry. So it's a second order system. And that is new, right? And so there's this relatively counterintuitive, again, for the time concept that if no force is exerted on an object, right, then they keep on going at their current velocity. And that's a little bit counterintuitive for us because there's friction all around us. So this is not really something that happens usually, right? If you kind of throw anything, for example, the movement will stop at one point. And so for a long time, right, the sort of intuitive idea was that the force would apply to the derivative in time of the position and not to the velocity. So the fact that we have a second order system is not entirely trivial. Now, of course, Newton builds on a lot of recent understandings, right, for the time. And in particular, I would be remiss in not mentioning the role that artillery played at that period, because people needed to calculate the trajectory of cannonballs. And they realized it was a parabola, so it's something that would come from a second order system. And then Newton says, okay, the time derivative of the velocity, right? It's the force. It's the acceleration. So force divided by the mass, and the acceleration in a basic case like that can be represented in the following manner. You sum over all other point masses, and then there's a force exerted by the point mass xj over the point mass at xi. And this force will depend, generally speaking, of their respective position, and there are physical constants in front of all that. So let me put for the moment something relatively vague here. All right. So that's the second very big step. And here, what you see is that we already have the kind of canonical many particle system that I'm going to be talking about. And it's also one of the first examples of an ordinary differential equation that was effectively written as an ordinary differential equation. And the third point, right, that is essential for us is Newton tells you what is K, what is the actual force. And that is the law of gravitation. And Newton tells you the following: the force is proportional to a constant, the gravitational constant, right? The product of the two masses, so mi, mj, right? And you see that here we have our physical constant, wij, right? And then it is parallel to the line in between the 2 point masses. It behaves like the inverse of the square of their distance. Right. And it's attractive, so it pulls toward xg. And that is the formula we have. Right. And this is a complete system. So, of course, now that we have a system, right, at the time, the question becomes, what do you do with it? Right? And what is immediate, right, is that this is a complicated system. But Newton says, well, wait a moment. I mean, it's not that bad, right? I can actually solve it if you have 2 point masses. Right. And that's because you can put yourself in the center of mass of the system, and then it's as if you had only 1 point mass, and there's a certain number of conserved quantities, and you can characterize all trajectories, right? And their trajectories are what we actually are very well used to now, right? So you can have ellipses, parabolas, or hyperbolas, right? So second degree conics, right? And they stay in a plane, and this is of course a huge bang at the time, because this is what people see in the sky. And the reason this is working relatively well for our solar system is that, of course, there is a very big dominant mass, which is the sun. And so you can get actually a fairly good first approximation of what's going on by looking not at the whole coupled system of the solar system, right? But simply looking at each pair of planet with the sun, right? And this gives you various ellipses, and then if there are moons around the planet, like our moon, right, then you can repeat the process locally on each planet, and again, what you think works very, very well for the kind of measurements that were available at the time. All right. In particular, right, there is something that is a bit scary in the initial system, and that stops being scary for this case n equal 2, and that is the singularity. Because you see that the norm, right, of k, as I said, behaves like the inverse of the square of the distance. And so in particular, it's something that blows up. If two masses get close. Right. Now, at the time, people know very, very little, of course, about well-posenness or this kind of notion for ordinary differential equation, right? That came much later in the 19th century. But they realized that there is a difficulty, right? In the sense that we might have a problem defining the dynamics if we have collisions between point masses. But for n equal 2, we have a very, very nice answer to that, because all solutions are explicit. And for n equal 2, we know this almost never happens. And actually, we know exactly when it happens. And I'm going to draw the picture because this is relatively simpler, right? So let's start at t equals 0 for simplicity, and right, and this is the line in between the two. The only case when this will happen is if the respective velocities are parallel to this line. So you need a configuration like this. And if the velocities are even a little bit off, then you don't have a collision. Right? So in our modern day language, right, what we could say is that this is a set of measure 0, right? So on a set of initial condition, of measure 0. All right. And, you know, for quite some time, people were reasonably happy with this description. But at one point, less so. And why is that? There's a whole set of reasons. First of all, we had much more precise measurements, right? So with more precise measurements, we realized that you could not ignore the effect of all the planets, for example, in the solar system, in particular, some of the very large ones. And so it really became necessary to try to put everything together, right? And so how do we solve a system like that for larger n? Well, now we know that there's not going to be an explicit solution. And so early on, what people used were numerical approximations, right? Or what we would call today numerical approximations. Through various expansions, right? And I'm not going to describe here how they are doing this. That's a little bit away from what we want. I will just mention two facts, right? One, this is how we got Euler method for solving ODEs, right? And second, this is, of course, people didn't have computer, right? So they were doing approximations by hand, and being able to do a good calculation was a very, very important point if you wanted to work in astronomy. But from a theoretical point of view, right, this was not entirely satisfying. But what people came to realize also in the 19th century and even later was that there was not going to be a much better solution. Right? So right? In particular, there's no way to really describe the long-time behavior of a system in a nice and synthetic manner, starting already with three-point methods, and that is the famous three-body problem, for example. That was solved by Poincaré in a negative manner, right? So showing that the behavior of a system is what we could call nowadays chaotic. What might be even more striking, right, from our modern point of view, is that we don't know if the dynamic is well posed or not. And this starts at n equals 5, right? So if I go back up a little bit, right, you see that for n equal 2, I have a very simple answer to the problem of the dynamic. It is all good except on the set of initial condition of measure 0, right? And this is something that you can extend relatively simply for n equal 3 and n equal 4. So 2, 3, 4, that works, right? And n larger than 5, no one knows. And the reason no one knows is there is a type of singular behavior, and you need at least 5 particles to do it. And we have no idea whether this is a set of measure 0 for the initial condition, or whether we can do this type of singular behavior on a positive set of initial condition. And the way you do that is you look at 2 pairs, right, of particles. Right. So that are going to orbit one another, right? So something like this, right? And then you take another pair here where they, right, orbit. Right, and you do that in a planar way, and then you use the third direction, the vertical direction, to have a 5th particle. And this 5th particle, what it's going to do is it's going to oscillate widely in between those two systems. And you time things so that every time this fifth particle goes through a pair, it takes a little bit of gravitational energy from the pair, right? So this increases its velocity, changes it into kinetic energy. That's what makes those oscillations go faster and faster. And because you take away the potential energy from the pair, right, the distance between the pair shrinks. And then there's a critical time when both pairs have a collision, right? And then the fifth particle is widely oscillating to infinity. So this is a very weird, type of behavior. But again, nothing that we can actually, that we know how to exclude. Right? And there was plenty of work until the 70s on that particular problem. All right, and so this is all very, very good, right? And that is at the level of our solar system. But then at some point, well, people realized how big the universe actually was. This took a while. But this is an important model in modern cosmology and astrophysics. And why is that? Because you're going to tell me, well, but we have general relativity, we have Einstein, we know that, you know, Newton's equations are not really working so well. But actually they are, because at large scales, the universe is reasonably flat. Right? I mean, if you go close to a black hole, of course, it's not flat at all. But if you take a much wider view, then the curvature is really not nothing that we can actually measure. And so in particular, that means that this system of coupled point masses remains a popular model to study the formation of galaxy or galaxy cluster. Which is, you know, very, very remarkable for a model that is again, more than 300 years old. And so this is, you know, this is again something that astrophysicists are using But they are using it in a very different way. That's because in that case, the number of point masses is much, much larger. Right, so we are done with you know, n equal 9 and n equal 10 or things like that, right? So okay. But this goes even further, right? A typical galaxy is said to contain the Milky Way, for example, is around 10 to the 11, right, stars. If you go to galaxy clusters, right, then this is going to be even larger. Now, of course, all of those numbers depend very much of you know, the cluster and all of this, right? But a galaxy cluster will sometimes contain up to maybe several thousand galaxies. So you add, you know, so that's 10 to the 14 stars, maybe. And this is even worse, as a matter of fact, because the kind of matter that astrophysicists apply these numbers to are very often not stars or matter as we understand it, but what is called dark matter. Now, dark matter is a bit of a controversial topic, even less so than dark energy. So the idea is that dark matter particles are a type of particles that only interact through gravitational interaction. So from a Mendelian point of view, right, they are a kind of a mathematician dream, because the Newton's equation, right, that I wrote above are actually completely accurate, because they are not going to have any sort of other interactions, right? So they don't have charges. So there's no electromagnetic interaction between them. They don't collide, right? They go right through ordinary matter. Now, of course, all of this means that no one has ever seen one, right? Because, well, in particular vision, if they don't interact with electromagnetic waves, you're not going to happen. So astrophysicists think they are there because they see their gravitational effect. And how many of them are out there? Well, if you go really crazy numbers, right, then you can, because in some models you can have up to 10 to the 60 dark matter particles that are predicted to exist in the universe. And this gives me the partial conclusion of this introduction, which is that now we are facing a very, very different fact, right? And we're not talking anymore about, you know, n equal 3, n equal 10, or anything like that. Now we are talking about absolutely enormous amount of particles. And so how we're going to handle a system like that is very, very hard. And that's really what the mean field limit is trying to give an answer to, as I will later explain. Right. And there are two questions that are actually tightly connected around that, right? Which is, can we represent such a system effectively? Right, so to perform analytical studies, for example, okay. And can we solve it numerically? All right. Now, what kind of algorithms we can have on this? Let me discuss that for 2 minutes. Now, if I ask you to do an algorithm, right, for Newton's equation, you're going to do a sort of Euler discretization, or maybe you'll use a higher order method. I mean, so some form of Runge-Kutta, maybe, whatever, right? So you'll discretize in time each of the trajectory. And then what happens is to update, right, the velocity of the particle I, you need to calculate a sum of n term, n-1 to be precise. And because you have n particles, right, that's n times n terms for every time step. And so if I ask you to do something like that, you'll come up with an algorithm which is in n square. And with an algorithm in n square, you're not going to do much, right? I mean, after you might be able to solve up to a few thousand, maybe 10,000 particles on a laptop, but that is not going to go further than that. Now, fortunately, we have more efficient method, right? And there's a type of algorithm that is especially popular, which is called fast multiple methods, that essentially do that in almost order n. So that's much better. Now you might be able to put in a few million, maybe a few hundred of million particles on your laptop. And if you go to a supercalculator, the best I have seen but we're talking about weeks of calculations on the supercalculator, right? is around 10 to the 13, 10 to the 14 particles. Okay. And so that's not 10 to the 60. And so what happens when you're doing these numerical methods, right, is there's a sort of intrinsic ID that is not at all obvious. And this ID is that if I can solve with a billion particles, then that will give me a good approximation of the system with maybe 10 to the 20. Right, so let's say 100 billion. But from a mathematical point of view, and until we learn more about that system, this is utterly ridiculous, right, as an idea. Because we're talking about systems of ODE. If I add even one ODE to a system, there's no reason in the world why the behavior should be similar. So why this should happen, right? Why we could have a good approximation of a very large system by a much smaller system with that's all sort of the same rescaled ODE is something that, again, if you come at it from the point of view of dynamical system, would be very surprising. But this works, right? In practice, this works very well. And so I can ask how to justify it. All right, let me make a 1-minute break here to see if there are any questions.
Yes, please don't hesitate to write down your questions in the chat place.
Nope. Everybody's good. Okay. Well, let's continue then. So after this relatively elementary introduction, what I want to do is I want to give you a few other examples of models. Okay. Now, I'm not going to give anything that resembles an exhaustive list, right? That's really not the point here. I just want to illustrate a few other settings, right? And we'll go to the still super old, super classical to the more recent. And Before I do that, I just want to say a few more words on the structure of our Newton equations. And I want to observe the following things, okay? First of all, the interaction derives from potential. Right, and that's because k, which is minus x over x cubed, right? This is actually minus gradient of 1 over x, right? And this is the gravitational potential. This is minus gradient of phi. And so those are often called Coulombian interactions. Because phi is answer is minus. Okay. Because phi is the minus the fundamental solution to the Laplacian. Now, I'm emphasizing this because this is a scaling that will come over and over again in our examples. So, you know, we might as well identify it from the start and not be surprised to keep finding it. All right. So this is a first point. The second point is, of course, that then this is a Hamiltonian system. And the Hamiltonian is the total energy of the system. And the equations follow from this system. Right. So if I list all the positions in a big vector Q, right? And I list all the velocities. Actually, let's put the momentum in a big vector P. I have that Q dot is the gradient of H with respect to P. And and I should put the, sorry, I forgot here the RG, MI, J, of course. And P dot is minus the gradient of Q of H. Correct. And so because this automatically preserves the total energy, right? So all right. And so this is a relatively classical system in physics that we'll find in several cases. All right. So let me check the chat. Questions? All right. So now I'm going to jump a little bit closer to the modern time, right? And by 1 century. So you know, it's not still relatively old, right? But this is a little bit more recent. And I'm going to take a very similar problem to the point masses, but now I'm going to look at charged particles. Right, so such as ions and electrons. All right, so this again remains very important in the modern time because they are the basics of plasmas. Which remain a key application. Now, of course, we used to have plasma TVs, and those are mostly gone, right? But plasmas are found everywhere. From, again, astrophysics, right, with clouds of charged particles, such as created by solar rays and all of this, right? Two very important questions in for the future of energy, because nuclear fusion, right, if it works, will rely on plasmas. So people who are building tokamak or other type of technologies, right, they need to understand the dynamics of charged particles. And so now what do I have, right? Well, I still have the mass, mi, the position, xi of t, the velocity, vi of t, but I also have a charge. And I want to build an interaction between all of those. And there's a very remarkable fact, which is that if the velocities are relatively small with respect to the speed of light, right? So if all those VIs are relatively small with the speed of light, the interaction between particles is purely what we call electrostatic. And what this means is that they don't create a magnetic field, right? There can be an external magnetic field. I'll add it later if needed, but it's not created by the particles. And it turns out that then there is a very, very simple law. So now very often I will use xi dot to denote the time derivative, right? And here I will find a system that looks very, very similar to the point charges. And instead of a law of gravitation, we have what is called Coulomb law, because this was written for the first time by Coulomb, even though apparently it was known a little bit before him. So this is 1785, right? Give you a ballpark of, again, when this was written. The strength of the interaction now is not proportional to the product of masses anymore, right? It's proportional to the product of charges. And K has actually exactly the same expression. But with a plus sign. So it's still a potential, right? But now phi is exactly the fundamental solution of the Laplacian. So you see, this looks very, very similar to Newton's law. We change the sign. Oh, I missed a question. Why is there a factor 1/n and be Hamiltonian? And there is not. Thank you. This will come later. So I jumped a little bit too far ahead. Sorry. Yeah, again, please don't hesitate to speak up, because I'm only looking at the chat once in a while. So again, I'll miss a question. Right. So this is still a Hamiltonian system. right? With basically the same type of expression for the Hamiltonian, but let me write it in full. So we could have essentially the same discussion as we had for Newton's law, right? There's one exception that I have to mention here. And this one exception is if all particles have the same charge or the same sign of the charge, right? And that's because then we have in H a sum of two positive terms. What does that mean for us? Well, that means a very simple estimate. Right, Qi, Qj, phi of xi minus xj, right? Which is so Qi, Qj, you know, 1 over, so there's a Colombian constant, xi minus xj, right? This is one of the terms, so it's less than the total, which is the initial energy. And so in that particular case, there are no collisions. So this is the one case here, right, when at least I can guarantee that the dynamics is well posed no matter what. Right, and you see you can't have a collision because you actually have a lower bound on the distance in between two particles. All right. So again, a very, very canonical example. I mentioned nuclear fusion, right? So in tokamak, what you have is you have a very large external magnetic field, right? Which you can add very easily. So you keep the same interaction term. And then you just add what is called Lorentz force. Right, and similarly here, I have classical particles because I've assumed that they are less than the speed, much less than the speed of light. You could add relativity correction if you wanted to, which I'm not going to do. All right. Any questions on this one? All right. Now, we are going to talk now about a much more modern correction, because now we are really jumping to the beginning of the 20th century with Einstein derivation of the Brownian motion, and actually the work of Ito after World War II for the way that we can write these things nowadays. But we are going to stick with point charges as an example. So I'm going to consider electrons and ions in a plasma. Now, the mass of the electrons is a lot less than the mass of the plasma, right? Mass of ions, sorry. And so what this implies is they are much faster. So at first approximation, it can be interesting to focus on the electrons, right? And assume that at the time scale of that the electrons will stop moving, right? Nothing much is happening on the ions. Okay, and if they are fixed, what can we say about their distribution? Well, we don't know. And so very, very often when we don't know, we are just going to say that it's random. So let's put them IID, right, identically distributed in the space, right? So now we want to separate our dynamics into two pieces, right? So let's take an electron, right? We would like to write something like this. Interactions with other electrons, right? Now, they all have the same charge, electrons. Okay. So it's something like that. But there is also the interaction with the ions, and in particular, the electrons will bounce back on the ions, right? So there's this other interaction, which are random collisions. On the background of ions. So how do we model those random collisions? Well, that actually took a while, really a while. To have, again, a first reasonable answer by Einstein in 1905, right? And then the correct definition of the stochastic integral and therefore the corresponding formulation of Brownian motions that you can get out of it by Ito. And the reason for the Brownian motion is what happens is, from the point of view of the velocities, is you have a random walk in velocity. And then this is translated into the movement in position. I'm going to be very, very rough in terms of the references here. François Cadmiel, if he wants. All right. And now I cannot write a time derivative of VI because VI is not going to be differentiable in time, strictly speaking. So this is in the sense of the stochastic integral and Ito stochastic integral. And I would have the following system. And the WI now are n independent Brownian motion because each electron will have its own sequence of random collisions which is supposed to be independent of a sequence of collision that another electron will see. And I'm not touching the equation on, there should be an MI. I'm not touching the equation on the, this can depend on I. I'm not touching the equation on the position, of course. So what we get here as a first variant is our first stochastic system. So this is a system of coupled SDEs, right? Stochastic differential equations instead of ODEs. And even though we started with deterministic system, in a lot of model, we don't really know what's going on. And so adding noise, adding stochasticity like that is extremely common. And actually, I should say, for this reason, stochastic systems are probably even more widely used than deterministic systems. All right, let's see. Any questions? Okay, then I think this is probably a good time to do a short break. What do the organizer think?
Yes. Thank you, Pierre-Emmanuel.
Right. So 15 minutes?
For 15 minutes. So we resume at 3:40.
Mm-hmm. That's good for everyone.
Thank you. If if the attendees have any questions, please write them in the chat room. For security reasons, we're not going to switch on micros because of the live broadcasting on YouTube. So if there are no questions, we meet again at 3:40. I have a couple of questions, Pierre-Emmanuel, but I will leave them to the end.
Okay.
I'm sure you will address them in between. Thank you.
See you soon. 15 minutes.
Okay, thank you.
I'm going to get a tea.
Okay. Pierre-Emmanuel, do you have
Oui,
some
j'arrive plus à démarrer la vidéo
issues?
parce que tu l'as bloqué. C'est pour ça que je suis dans les participants, là, en train d'essayer de voir si j'arrive à me débloquer tout seul. Mais
normalement, tu es co-animateur. Je vais te
oui,
remettre
mais sur la tablette, pas sur le PC.
Ouais. Tiens, bah, attends, je dois pouvoir te nommer. Ah non, il n'y a que toi, Abdou, qui peut le faire, je pense.
OK.
Ouais, c'est bon.
Oh,
Okay,
sorry
super.
for this.
Non, non.
I forgot you had to introduce. Merci.
Okay. Any questions from anyone?
So maybe I have a very short question. I think maybe you will address it anyway. But when can we term K as a short, mid-range, or long-range interaction kernel? And so the next question is for short-range interaction kernels, is it possible to reduce the sum for J's which are neighbors of I only? Thank you.
All right. So for your first question, it really depends what you call long range, short range, and medium range. I have not discussed scalings yet. I will do that at the end this morning. In the electrostatic case, for example, you have this notion of screening, right? Which is that the electrons, for example, might not be able to really see electrons that are super far away because the total charge of the plasma is zero. And so after sometimes you have ions, you have electrons, everything is mixed. And so this average out and they don't see any force coming from very, very far away. So you have models like that screen the interaction after a certain distance. And that distance is in terms of the fluctuation in the plasma. I really don't want to try to write it down here. So this can screen out the long-range interaction, but long-range in the sense of far away enough for some scaling that is inherent to the plasma. This might not lead to a very big simplification in the sum because this range might still include most of the electrons, or at least half of the electrons, for example. So instead of having a sum over n terms, you might have a sum over n over 2 terms, right? At the other end of the spectrum, though, you have the so-called hot sphere gas, right? Which is a gas of hot sphere, and so they do not interact until they collide. And when you have a collision, it's an elastic collision. And this has been a very popular model for gas dynamics from the 19th century, actually. And it leads to collisional models, not mean field limits, so a Boltzmann type of equation instead of Vlasov. And here you have what is really a purely short-term collision, short-term interaction, because you need a collision, right? So you need the distance between the two particles to be very, very small, of the order of their diameter, for anything to happen, and otherwise nothing happens at all. Now, if you have something like that, then it does simplify a great deal of the sum, because with probability 1, actually, you can only have collisions between two particles. You cannot have free particle collisions. So that means that in the dynamics of one given particle, it will only ever see at most another particle at any given time. So I'll come back. I'll try to come back to this one once I discuss scaling in half an hour, and hopefully it will be a little bit more clear. All right. One thing I want to emphasize here with this system of electrons is another remarkable and new structure that emerges for that model. We have what is called an exchangeable system. And that's because all electrons are physically identical, right? They have the same charge, they have the same mass. So the only difference between electrons in their equation, right, is their starting position and velocity. And consequently, so I should move here. Consequently, right, if you look at this system, you see that I can relabel it as I want, right? So I can swap two electrons and it makes no difference. And that's why we call it exchangeable. And this is a very, very important case because we will see that we know a lot about the mean field limits for exchangeable system, and we know very little for the mean field limit for non-exchangeable system. Questions? No? Okay. Let's keep jumping centuries, right? So we had low gravitation, 17th century, then we had Coulomb law, 18th century, and now I'm going to jump to the 19th century, and we'll finally reach modern times, right? With another very classical model, which are point vortices. And this is a formulation due to Helmholtz around the 1850s. And we start from a fluid in dimension 2, right? So let's look at the incompressible Euler. in dimension 2. And in dimension 2, there's a very remarkable fact, which is that you can simplify the incompressible Euler equation by looking at the vorticity. Which is the curl of U. So it's D1U2 minus D2U1. And that's because when you take the curl, you get rid of the pressure, which is the one thing that you don't know there. And in dimension 2, there's a bit of an algebraic miracle. And in the U grad U, which is the nasty nonlinear term, keep a very simple form. And you end up having a transport equation on the vorticity with the fluid velocity. And moreover, U can be calculated from omega by the Biot-Savart law. And that's just the remark that we know the curl of U and we know its divergence. And therefore, what we have is the following formula: U of T and X is a convolution with W, and our convolution kernel is something that we know very well, because it's basically, again, our Coulombian interaction, but now in dimension 2, so you have a 2 instead of a 3, and you rotate it by pi over 2, right? So x orthogonal is minus x2, x1. All right, so this is a relatively simple formulation that is very, very useful for studying fluid equations in dimension 2. But for us, it has led to a different type of model, which is we had point charges, now we can have point vortices. So Helmholtz proposed to concentrate the vorticity on points, just like we concentrated the mass on points, right? Or the charges on points. Now we are going to concentrate the vorticity on points. Right? So I will have the vorticity Wi, and I will have the position of each vortex xi. And then it turns out that they did a few algebraic calculations and it came up with the following model. Which is again a mini particle system. And at the time, Elmos was hoping to use this to better understand what he was calling turbulence. We would be nowadays a bit hesitant of saying the word turbulence associated with a two-dimensional flow, but certainly understanding instabilities in fluid then would be fairly accurate. So this again remains a very important model when studying fluid dynamics nowadays. And it is remarkable in a few ways. First of all, it's still a Hamiltonian model. There's no velocity, of course, anymore, right? This is a first-order model. And so the Hamiltonian has a much simpler type of equation. With phi, which is the fundamental solution of Laplacian in dimension 2, so it's log, right? And for this to be a Hamiltonian model, the simplest way is to actually multiply everything by Wi so that you have now a symmetric expression, basically. Moreover, now this is a first-order model. But still with a singularity. And now you might think, well, it's very much the same, right? Because the singularity is, again, when we have collision, right? So when xi is equal to xj, so a very similar type of problem of discussion that what we had with Newton's equation. But you would be wrong. And that's because this is actually a nicer singularity. And what happens here is xi is everything we have, right? So if I look, I pick two particles, right? And I look at where the singularity is in their dynamics. Okay, so here I have, right, let's represent this by a line, right? Xi minus xj, right? So this is the first coordinate, and then the second coordinate. And the singularity is exactly at the origin. For Newton's equation, however, and now I have to add the velocity, right? So now I cannot really do the drawing in 2D, but since I'm horribly bad at drawing in dimension 3 and even worse, dimension 4, right, I'm going to project over 2D. So our horizontal axis is actually going to be a plane, right? or maybe a three-dimensional space, and this will represent the full difference xi minus xj, and the vertical axis here will represent the difference of vi minus vj. So again, this will be a plane or a three-dimensional space. And the singularity now is not at the origin. The singularity is along the whole vertical axis. Right? And this is because you will have a collision if xi is equal to xj, no matter what the difference in the velocity is. And at this point, we'll remain at a very naive formulation of that, but what you see out of this is that it's far more likely that you will hit the singularity for Newton's equation than it is likely that you will hit the singularity for a first-order model. Okay. Now, this is the deterministic case, right? We can have a stochastic point vortices just by adding Brownian motion. So then I would have a system like this. And what we would expect in that case is that this should correspond in some sense to Navier-Stokes instead of Euler. So the random collision among the point vortices should model some sort of diffusion in the system. Any questions? Okay. Let's go to the 20th century. And let's discuss some elementary, very rough model of chemotaxis leading to the Keller-Zegel system. Okay, so chemotaxis is a Greek term, right? And it refers in biology to the dynamics of microorganisms, such as cells or bacteria, under the influence of chemical signals. So it's the movement of microorganism. All right. And this is actually how cells or bacteria communicate, right? Through chemical signaling. So this is a key element if you want to understand anything to the actual complex biology in plenty of cases. And so a very important example that is still not completely understood, right, is the question of the formation of blood vessels around tumor. Right. So if you have a tumor, and then where several is when it's cancer, of course, right? And this is growing, and to grow, it needs a lot of nutrients, it needs oxygen, it needs all of that, right? And past a certain size, it's relatively clear that there are not going to be enough nutrients naturally around it. So the growth would stop, right? Which is would be great, right? Which would be great, because that would mean that the tumor couldn't keep growing, right? So perfect. But what happens is that tumors in that case start emitting chemical signaling, right? And the cells that form the wall of blood vessels react to that and start building new blood vessels toward the tumor to increase the amount of nutrients that is available, right? This is called angiogenesis, and this is the important way in which cancer keep growing. So again, this is something that we would love to be able to control. So now our particles, right, would be cells. And cells are very complex objects, organisms. Certainly much more complex than a point mass, a point charge, or a point vortex. So whenever we go there, the modeling becomes a lot harder because there are so many phenomena that are coming into play and that you cannot really take correctly into account. So what I'm going to do now in well, essentially 5–10 minutes is something extremely rough, right? If you're interested in that, there's actually a huge literature in correctly modeling angiogenesis and correctly modeling chemotaxis, right? This is not it. but it will give you the scale of what's going on, and it will bring us to a very simple many-particle system that is going to be very similar to the ones we already have. All right, so what am I going to do? I'm going to say that the cells are points, okay? So again, I will have point cells, I guess you should say, right? So I'll just represent them by their position, xi. Okay. And I'm going to say that there's a certain amount of chemicals in the environment. Right. With a certain concentration, right? And so let's denote those concentrations, C1, right, of T and X, and so on, right, till CK of T and X, right? And now I'm going to say that each cell follows the concentration. And the gradient of concentrations. So I have a very basic dynamic, right? Which is going to be simply that dxi, right, is going to be the following, this. And maybe, you know, the cell is more sensitive to some concentrations rather than others. So we'll have chi1 gradient of C1, right? And so on, plus chi k gradient of CK. And the concentration, where? Well, the concentration at the location, the gradient of the concentration at the location of the cell. Txi, gradient CK, Txi, right? And I'm going to add diffusion. Again, in a very rough manner, just because we basically don't really understand what's going on. And on top of that, many bacteria have what we call tumble mechanisms, by which they randomly switch the direction in which they move. So we get to a model like that, right? And now the chi-I, they could be positive, they could be negative, right? If the cell wants to avoid a certain chemical substance, right, then it's going to move away. And if it likes a chemical substance, then it's going to move towards it. So a very basic model, what's missing, of course, in all that is an equation on the concentration. Right, so I need an equation on C alpha. And generally speaking, I will have a diffusion equation. So something like dt of C alpha, and let me scale this, right, with the inverse of the speed of diffusion, minus Laplacian of C alpha, right? And then the concentration is produced, right? So there is a source, S alpha, right? And it is produced by the cells themselves, right? That's how they communicate. They produce the signal, and the signal is read by other cells. So if they produce it, and the cells are points, right? Then I have to add, and there's going to be the rate of production, I have to add Dirac masses into the equation for C alpha. And an immediate simplification that I'm going to make is I'm going to say that epsilon is smaller than 1, and that means that the chemical C alpha is diffusing much faster than the cell are moving. And this is not unreasonable, but it's not always the case. Still, I'm going to make this assumption here, and therefore I can get rid of that. And now I have an elliptic equation. And so if I have an elliptic equation, what do I have? I have that C alpha is equal to phi convolved with S alpha plus P alpha, the sum over I equal 1 to n of phi of x minus xi. And phi is the fundamental solution to minus Laplacian. And what does that tell me? If now I put everything into this, so I have a certain given force, right, that depends entirely from the environment. So this is given, right? And then in that relatively simple case, right, I have this interaction. So J xi minus xj. And let's say that I'm in dimension 2, right? So this now would be k, right? And so in dimension 2, phi is again minus log of x, and k would be minus x over x squared. So it is almost exactly the same system as point vortices. Right, I have k, which is minus x over x squared, versus k, that is x orthogonal over x squared. So you see, that's really fascinating how we always end up with very similar scaling, because underlying all of those derivations, right, there's this Laplacian that shows up again and again. And this is because diffusion, right, and Poisson equation are so fundamental in physics and chemistry. So whenever we deal with this kind of phenomenon, then they often appear, right? But this is Hamiltonian. Right? And this is a gradient flow. And that is actually a huge difference in behavior. So now we find our last type of structure, right, which is with gradient interactions on first order system, right? And they are not Hamiltonian, they are dissipative. So the energy is not going to be reserved, the energy is going to be dissipated. And this is a whole class of itself and hugely important as well. I'm not going to give you more examples because I think this is going to be enough. But again, there's a huge literature on gradient flows on their own. Any question here? Nope. All right, let's go to my last example. In neuroscience. And so now I'm interested into the dynamics of neurons in the brain. Now, the same type of speech that I made for the chemotaxis case, right, I should make here, except I'm not going to repeat it. So again, those are very, very complex. So what we're going to do here is extremely rough. So we're going to represent an individual neuron, right, with its activation potential, which is the electric potential on the membrane. So I'm going to call that AI of t. And so we need an equation on those AI, right? And what happens is most of the time we are going to assume that it's something extremely simple. And here I'm even going to take an ODE. You could take an SDE, so you could add noise if you want, right? I'm just going to assume that right, the membrane potential grows in a certain nonlinear way most of the time. You can add a Brownian if you want to. And then neurons can fire, right? So with a certain probability that depends on its current potential, and the higher the potential, the more likely it is, a neuron fires, right? And what happens if this takes place? Two things happen. This resets the potential, right? And so let's say that it resets it to 0 for simplicity. And then this activates the neurons that are connected with the neuron I. So if a neuron J is connected to I, then there's a small jump on their potential. Right. And so if we fire at some time t0, then immediately after, right, you have something like this, some learning rate and some Wij, right? And Wij measures the influence of neuron I on neuron J. So it could be positive, it could be negative, right? Because some neurons activate other neurons and other neurons inhibit them, right? So the sign can change. And of course, they need to be connected. So in general, this is an extremely complex map. So what you have here is a purely stochastic system, right? It's almost pure germ process, except for the first equation, right? Around a complex stochastic system. Now, formally, I can still write it as we were, right? So I could still write that, you know, AI dot is equal to some function of AI, right? Plus the result of the activation, right? But here I have a relatively complex stochastic term, right? And here I should put as well, right? This is what's going to bring it back to 0. And it's a complex stochastic term that is concentrated on Dirac masses in time. So I'm not going to be much more precise with this model, because otherwise I would spend the next half an hour on that. I wanted to write it down to show you now a very different type of application, right? Because this is neuroscience. one. Second, a different type of singularity as well, right? Because in all the previous model that we've had, the singularity in the interaction, right? The interaction depended on the position, and the singularity was when the two positions were identical, so when there was a collision. So it was a singularity in the physical space, right? And here what you have is more singularity in the time dynamics. Okay, this is it for the model. Any questions on any of that? No? Okay. Last item this morning, in this very long introduction and motivation, right? Let us discuss the scalings. And finally, get to this notion of mean field and mean field scaling. And first of all, let me summarize the number of particles. Right. And we've had quite a few applications, so let's look again at how many particles we would have in any of those applications, right? So we started with Newton's law, right? And this is astrophysics. And we said from, you know, essentially 10 to the 11 to 10 to the 60. Right? Very wide range. Then we had the point charges, right? So plasmas. How many particles do we have in the plasmas? How many ions, how many electrons? Well, in a typical application, that is going to be around the Avogadro number. So 10 to the 20 to 10 to the 25, something like that. Still very, very, very large. Now, point vortices, it really depends on, and it's typically up to 10 to the 12 for practical purposes. A chemotaxis. Okay, so we have a biological population of microorganisms. How many are we talking about? Again, right, we could do a whole class on this, on the sizes, on how the population sizes in various biological application. So let's talk bacteria, for example. Let's say you have an infection, right? What would be the number? Typically, if it's less than a few million, you probably won't feel it yet. And it's probably not going to be detectable in your blood, for example. And above 1 trillion around, well, you're probably dead or very close to. Right? So that gives us a sort of reasonable range of the size of the populations, again, that we want to consider. And neuroscience, right? How many neurons do you have in the brain? a little bit less than 100 billion. Now, of course, that's going to be very, very dependent again on the application, which animals we are talking about. Are you trying to model the whole brain? Probably not a great idea, right? Or are you just going to look at one particular region of the brain, in which case the number can be much lower? Okay, so that gives us a ballpark. And you see that in physics, right, the numbers tend to be larger. And in biology, the numbers tend to be lower. But in all cases, this is still very, very big. So we really want to do something with those systems of coupled ODEs or coupled SDEs and change them into something that is a little bit more attractive. Okay. Let me go back to our second order Newtonian dynamics to give you an example of how we scale. Scaling, how we scale a system. Right. So we start with this. And I'm going to write it down in a somewhat abstract way, like that. And we have initial conditions. I can rescale in position, right? And I can rescale in velocity, and I can rescale in time. Right, so I can introduce the scale L. I can, in velocity, the scale V, and in time, right, the scale T. Right. So I can go back to, you know, rescale quantities. So xi bar, right, would be 1 over L of xi at time t, right, at the rescale time. And now I can write a system of equation on those objects. So xi, d over dt of xi bar, right, you see is 1 over lt, right, d over dt of xi. So it's 1 over lt vi, right, vi at t over t, and vi now I want to change it into vi bar, so I need to divide by v, and therefore I need to multiply by v. No, I'm sorry. If I put, I messed up my notation. T should be tau. It's an inverse of a time. Time scale tau. Okay, tau. Oh. And then I can do the same thing with VI bar. And I get the following equation. And how do I choose all those scalings? Well, I choose them such that, let me check, there's nothing in the chat. Hope there was a question. I choose them such that initially the positions are mostly of order 1, and initially the velocities are mostly of order 1 as well. Right, so this fixes L. It fixes V. And I don't have a choice for tau either, because if I want to keep something that looks like Newton's law, right, I want to choose tau such that x bar dot is equal to V bar. Okay. And I obtain a rescaled system. This is gone. And here I have parameters. And so what you have here, and you see that there are the physical constants, right, in these systems as well. So when I'm doing this, what you see is that depending on the initial condition, I can have any sort of scaling in this system. Right? V tau could be very large, could be very small. L could be very small, could be very large. Right. On top of that, you know, it might get out, right? And here again, I have physical constants that I should add in here, right? The Wij, right? So it's whatever it is, right? So if K is a Coulombian interaction, in dimension 3, I would get the corresponding system. Xi bar equal Vi bar dot Vi bar dot, right? Would be this Wij, and then this behaves like 1 over x minus xj to the square, right? So 1 over V tau L square. Okay. And we get a zoology of system depending on how large this Wij divided by V tau L square is. And this is a simple case, right? This is a simple case because K is homogeneous, so I can actually pull out this L and put it with everything else. But if K is not homogeneous, so if I have point charges and I have a screening, right, then this is much more complicated. Right. So now we come back to Abdul's question at just after the break, right? So let's say that K of X now is not the pure Coulomb, right? But is being screened at some distance. Then you have an even more complex interaction between my rescaling capital L, right? And the scale of the screening small l. But let's say it's homogeneous, and let's say that I have this system, right? Let's give a name to this constant. Let's call it 1 over m, for reasons that are going to be obvious. Then formally, there are 3 regimes that you can identify. You see that here you have a sum of n terms, right? Now, this is formal because, of course, K has a singularity, so all right, those terms might be unbounded if you have collisions or anything like that. But again, let's keep it formal, right? I have a sum of n terms. So if m is much larger than n, right, then this sum should be very small. So then we would expect that vi bar dot would be much smaller than 1. And this is not a very interesting dynamics, right? And it means that at those scales, right, at those time scales, nothing much happened. And you would expect that this system is correctly approximated by having free transport, so just letting each particle evolve independently, right? A third regime, right, is when m is much less than n. And in that case, now we expect this sum to be very, very large. So that means that now we would have either huge oscillations or very strong constraint. on the relative positions, right? To keep the sum smaller than it should be by building cancellations, right? Between terms in the sum. This is very hard, right? This is the regime that you would have if you wanted to derive the dynamics of solid, right? Because, you know, solid, the table, right, it's made of atoms. So in principle, right, we should be able to derive the equation of motion of a solid from first principles, from Newton's equations, by putting the right force terms and the right scalings. And this is very, very hard, right? And you see the kind of constraints that I'm talking about, because then you would have to have this crystalline structure that is inherent to solids so that you have those cancellations. This is obviously mathematically hard. And then we have the miracle case, where M and N are similar. And this is the mean field scaling. Right? So this is the scaling that we are going to try to understand. And as usually say, it is the easiest interesting scaling that you can put in a many particle system. And that's because there it makes the sum formally of order 1, so you can expect to have something interesting. The I is going to change, right? But it's not going to change so fast that it will be very, very hard to control. So that's what we are going to focus on for the rest of the week. And of course, this discussion again, right, is in the simplest case where K is homogeneous. Oh, let me repeat that. If you have screening effects, if you have anything else, right, K is not going to be homogeneous. I could not have such a very simple description, right? And so you have more scalings in complex settings. Such as collisional scalings. For the Boltzmann-Grad limit. Which I'm really not going to talk about. All right, this is it for today. I will take any questions you may have.
Thank you very much, Pierre-Emmanuel. I will switch on for all attendees to reactivate their micros if they want to ask audio questions. And written questions are also, of course, welcome. So if you have any questions and would like to ask by micro, feel free to reactivate your micro, please, and ask the question.
I think everyone is dead or has understood everything.
There is one question, maybe.
Yeah, go ahead.
Can you hear me?
Yeah.
Oh, sorry. Sorry, can you hear me now?
Yeah.
Thank you for the introduction. First, could you please provide us some references or some application for this?
So there's a long list of potential reference.
Maybe one or two.
For the discussion today, I'm going to send you to reviews. So I have two reviews myself, one with my students specifically on stochastic system. There's also a very nice review by Goltz. And there's the classical book by Spohn, which is a little bit older now, but on all the physics model, because they have not changed so much, it's still very good. Anything else you wanted to know?
Yes, I have a question, but just to find myself, if I understand well, this is from for the case when the particles or when agents cooperate.
Not really. So the notion of cooperation, of competition, right, is more in the economics field or ecology. It's relatively hard to say in a physical system whether you have cooperation or competition. It's not exactly the right notions for this. Of course, I couldn't describe all possible applications, right? So I had to make choices here, and I decided to ignore applications in ecology and in economy. But you do find a little bit of this notion of cooperation or competition in this model in neuroscience between neurons, right?
Okay.
And it's not exactly that. But you find a little bit of that, right? So if Wij is positive, you could say that neurons cooperate in the sense that they reinforce each other.
Mm-hmm.
And if Wij is negative, however, they don't cooperate, right? They are antagonistic in the sense that one is trying to inhibit the other one. And so this is more, it's not exactly competition, right? So this is a very rough way of formulating it, but it's more akin to competition. So what you see here is that it's not really that the models are built for competition or cooperation. It's just by switching the signs of the coefficient, you can have competition or you can have cooperation. Does that make sense?
Okay, yeah, thank you, I understand now. So there is no conditions for agents or
conditions for what? To be cooperating or to be competing?
No, to use these models in general. So, like,
there's a long list of conditions on each model for it to be even remotely valid, right? Again, if I just stick at that level of neuroscience, you have a huge literature, and you have all sorts of models that people have been deriving just for this, depending on what they think are the correct conditions on the neurons, on the dynamics, on the timescales. Right. So those are just examples that seem to apply relatively well in at least one situation.
Mm-hmm. Okay. Thank you so much.
Are there any questions? So, Pierre-Emmanuel, if I understand, the scalings L and tau are can be controlled with zooming in and zooming out, and like recording fast or slow what you observe. Well, what I learned today is that, because I was wondering, since it is a question of observing the dynamics, what is the good M? And what you told us at the transitional conclusion is that if I can zoom in and zoom out and record slow or fast, then there is a narrow band in scaling for velocities, which leads to the mean field limit.
Yes, absolutely.
Okay.
And that's very, very important, especially in all those physical applications, because sometimes people feel like the mean field scaling and the mean field limit is very natural and it's always going to happen. No.
Yeah.
No. It's a little bit more true for first order model, right? So if I had removed the equation xi dot equal vi dot, because then I wouldn't have this connection between DL and tau, right? And so I would actually keep the freedom of the time scaling.
Okay.
So for first order model, it's actually easier to go to the mean field scaling because you have one additional degree of latitude. So if the interaction is homogeneous, for example, in first order model, I can always choose the time scale in order to have the mean field scaling. But for second order model, this is absolutely not true.
Okay.
It's still very useful, but you're not going to understand all the laws of the universe and all the physics in the universe, even if you understood all the mean field limits.
Okay, I understand this. Are there any other questions? No? Okay.
Let me just ask one last thing to everybody before tomorrow so that I can adjust. Was today too fast? Was it too slow? Did you already know all of this? I mean, what was the level in comparison to the expectations?
I think this was really good. This is my feeling. I think that this was really good. If anyone wants to say something, for sure, this could be really useful for tomorrow and the next lectures. But on my side, I think that this was really good.
Well, let me from up something.
Yeah, somebody says that this was perfect. Yes.
Okay. Look, I'll keep going according to plan then, but I'll ask this question every day. So if you feel that one day is going too fast or too slow, you can still change your mind.
Just two questions, Abdou and Pierre-Emmanuel. For the notes of the lectures, do you have in mind to share this? I don't know whether you had in mind to do that, Abdou. Do you think we could post this on the website? If Pierre-Emmanuel is okay, for sure.
Yeah.
If Pierre-Emmanuel is okay, at the end of the 4 sessions, we can get PDF of Pierre-Emmanuel, and François, you could upload it to somewhere.
This would be really nice, yes.
Yeah, and I will also summarize, give you the four links for the lectures which are posted on YouTube.